Hello students. Today we're going to talk about the average rate of change of a function, which we sometimes abbreviate ARC. And what we're going to do is we're going to start with an application, an example, that will help motivate this topic. And we're going to talk about speed, and specifically average speed. I think we're all familiar with the concept of speed. It's about how fast we're going. If you drive, for example, 120 miles in 2 hours, we can actually calculate our average speed pretty easily. The average speed is just the distance we've traveled divided by the time it took to get there. So the distance was 120 miles, and the time was 2 hours. 120 divided by 2 is 60, and since we're dealing with miles and hours, this is 60 miles per hour. We don't know what the speed was at any given moment. It could be that we drove 60 miles an hour the whole time. It might be that we started off more slowly and then we got onto a freeway where we could go faster. There's lots of ways that we could have achieved this, and we don't know our speed at any given moment. But if we know that we've traveled 120 miles over the course of 2 hours, we can calculate our average speed as 60 miles per hour. Now, what I want to do is consider a situation where we're driving a car and we want to figure out our average speed. If we look at the speedometer, that will tell us how fast we're going at a particular moment. But if we speed up and slow down, that information isn't very helpful to figure out what our average speed was over the course of several hours. So what we're going to do is we're going to rely on the mile markers that we see along the side of the freeway as we're driving, and that will tell us our position on the highway as a function of the time when we pass by those. So this is going to give us some information about our position as a function of time. So t will represent time. We're going to represent the position function with the letter s. This is fairly standard in mathematics. I don't actually know why, to be honest, but oftentimes position is represented with the letter s. And so let's pretend that we get on the freeway at time 0. That's our starting time. And we start at the very beginning of the freeway, which is mile marker 0. Then, after 1 hour, we notice we're at mile marker 50. At 2 hours, we notice we're at mile marker 75. At 3 hours, we're at mile marker 140. And at 4 hours, we're at mile marker 200. We know that our position is a function of time, and this is a scenario where the only way we can express this function is numerically, because we don't have an equation that tells us our position as a function of time. We don't have a graph. We just have the information that we took by observing the mile markers at certain times along our journey. And so what I want to do using this information is I want us to find our average speed from t equals 1 to t equals 4. So we're looking between 1 hour into our trip to 4 hours into our trip. We could also express this, instead of saying from t equals 1 to t equals 4, we could just say on the interval from 1 to 4. This is basically saying between hour 1 and hour 4. Either one of these is the same way to express the same idea. So we want to find out how fast we were going, what our average speed was on this interval of time. And we're going to use the formula for average speed. So this is average speed. It always equals the distance traveled divided by the time elapsed. This is a formula that's always going to be true, whether we're driving, whether we're running, whether we're looking at minutes or hours. And the way that we do this, to find the distance traveled between these two times, we have to look at the positions and we have to take the difference. So it's going to be our position at hour 4 minus our position at hour 1 divided by the amount of time that has elapsed, which is going to be 4 minus 1. Another way of thinking about this, the numerator here is the change in position, and the denominator is the change in time. And we're looking at the change of something between two quantities, we've got to take the difference. Now, we can look at the positions. Our position at hour 4 was 200, minus our position at hour 1 was 50. And then in the denominator, we've got 4 minus 1, which is 3. 3 hours have elapsed. Now we can do the subtraction up top. 200 minus 50 is 150. So we have 150 divided by 3, which is 50. And our units here are miles per hour. So between hour 1 and hour 3, our average speed was 50 miles per hour. Let's do the same thing, but let's look between hours 2 and 3. So let's find the average speed on the interval from 2 to 3. So again, to do this, we need to find the change in the distance, which is represented by s of 3 minus s of 2, over the amount of time that's elapsed, the change in time, which is going to be our ending time minus our starting time, so 3 minus 2. It might seem weird for you to write it out like this, when you could just look here and figure out the distance that we've traveled and the time that's changed over that interval. But I want to do it like this because this is expressing it in terms of our function, and we're going to be looking at functions more later, so I want to get in this habit. So s of 3 is 140, s of 2 is 75, and then in the denominator 3 minus 2 is 1. Now 140 minus 75 is 65, and we have 65 divided by 1, which is 65, and again, we're measuring in miles per hour. So it looks like we were going a little bit faster between hours 2 and 3 than our average speed between hours 1 and 4. If we wanted to, we could do these calculations for any other interval between these values of t, but this is all I want to do right now. In the next video, we're going to look at this more generally. Instead of looking just at speed, we're going to be looking at rates of change. We'll develop a formula for the average rate of change of a function, and we'll look at a numerical example.